Hello, guys. So today we're gonna dive deeper into a subtopic of enzymes, which is the Michaelis Menten Equation. Now, the Michaelis Menten Equation, it deals with explaining how the initial reaction velocity, or the initial rate of reaction, is of an enzyme catalyzed reaction is dependent on the substrate concentration. So when I say it like that, that's a mouthful. That's a lot. But we're going to break this down and we're going to talk about the few things that make up the Michaelis Menten equation. The first of which is the Vmax, and the second one, which is the Michaelis constant, Km. Now, Vmax is the theoretical maximum rate of reaction or velocity, and Km is the substrate concentration at which, so I'm writing the substrate concentration like that, at which we have half of Vmax. Basically, it's the concentration, the substrate concentration at which half of Vmax is achieved. So half of the maximum rate of reaction, the concentration that happens at is the Km. But before we kind of dive deeper into this, I want to introduce a few things. One of which is explaining how enzymes work. So the first thing we need to know is that enzymes are what? Are proteins, correct? And they're tertiary or quaternary proteins. That means they have polypeptide chains, and when they arrange themselves, they form some sort of depression, which we call an active site. Now, at these active sites, what you can imagine is, if this is your polypeptide chain, let's say this is your polypeptide chain, you'll have a bunch of like R groups sticking out, right? And so when these polypeptide chains, they mix together and form, like, let's say, an active site. Let's say this is the active site. Let's say this region is the active site. You'll see a bunch of maybe R groups, maybe some other chemical groups sticking out. And effectively, when we say an enzyme binds to a substrate, it's these R groups, or these chemical molecules, or chemical species on the enzyme that will react with either a chemical species on the substrate. So if this is our substrate, it will maybe react with, let's say there's like an OAH sticking out. So this R group might react with this OOH, and they kind of sticks it together. So they're kind of binding and sticking together. But another thing is also the geometry. So when these active sites, when they bind to the substrate, they're not just doing it based on like bonding, but it also depends, the bonding is encouraged by the geometry. So if the shape isn't the correct shape, then they're not likely to bind, right? Like there's a lot of nuances in how this exactly happens, and that's why it's selective. But what will happen is the substrate, if it has the complementary shape, to the active site, it will form what we call an enzyme substrate complex. And what this enzyme substrate complex does is that it holds the bonds of the substrate in such a way that it adds stress onto the bonds. So what this means is, if I have, let's say, a sucrose molecule, and this, let's say this is a sucrose molecule, then when this enzyme holds the sucrose like this, what effectively it does, it will add stress to the glycosidic bond, which is holding the glucose and the fructose together. It will add stress to that glycosidic bond such that you won't need as much energy, right? You won't need as much energy, less energy required, to break this bond. And that's how an enzyme catalyzes a reaction, right? That's how an enzyme catalyzes a reaction. It will hold the substrate molecule in such a way that the bonds, the energy required to break the bonds is decreased. So if you then look at what actually happens, to the activation energy, that's exactly why it drops, right? If this is the activation energy, EA, then with an enzyme, it is significantly lower. And this is because of what I just said. That it's because of how the enzyme holds the substrate in the enzyme substrate complex. And so this will then lead to the creation of our products. So let's say this is these are our two products, right? And so what we need to understand right now is, okay, I get it. So there's a few steps to this. Step 1 is the substrate binding to the enzyme. Step 2 is the enzyme substrate complex being formed. And then step 3, which is what we see now, is the products forming. And so when I think of these steps, I can think of explaining all of this in terms of what? In terms of maths. So let's say step number 1, substrate finding the enzyme. Step number 2, the enzyme substrate complex forming. In step number 3, where the enzyme is reused and basically comes out of it unscattered, whereas the products are now formed, right? So in the case of sucrose, you'll break down into fructose and glucose. And so how am I going to describe this in mathematical terms? Well, it's very easy. It's enzyme plus substrate leads to the formation of enzyme substrate complex, leads to the formation of enzyme, so enzyme for reuse, and product. Right? P. Which is P. If it can go forward, it can also go backwards. Because all of this is just about probability. Which brings me to my next point, which is, how exactly is step 1 happening? Step 1 is happening because of something we call collision theory. I'm going to call this equation 1. I'm going to come back to this. Now, collision theory is very simple. It's basically saying that when you have an enzyme, let's say I have a box, right? Let's say I have this massive box. And let's say I have my enzyme, I have one enzyme in it, which is, I have one enzyme, and then I have one substrate. Now let's say they're at opposite ends. Okay, so I'm just going to redo this one sec. Yeah, okay. So let's say this is my box and that's my enzyme and that's my substrate. Now, how likely, if this is all moving in random directions, how likely is this substrate going to find this enzyme? It's not, the probability for this isn't as high, correct? Right? That makes sense, right? If you have one enzyme and one substrate, finding each other that becomes difficult. So the probability of this E plus S happening is low. Now, if I increase the amount of substrate, so if I increase the amount of substrate and they're all moving in random directions, right? I've kind of increased the probability at which this collision can happen. The collision between what? The collision between this enzyme and this substrate. It's increased. So collision theory is effectively how enzymes work. Increase chance of collision. When I say chance, I mean probability, right? So that's effectively how enzymes work. They work because the substrate needs to find the enzyme to form this enzyme substrate complex. And so if I have more substrate, I can bump into my enzyme with a higher probability, and that can lead to the remaining of this equation, right? The formation of the ES complex and then breaking down of that into enzyme and product. Now, earlier I mentioned that, okay, the substrate has to bind to the active site either through interaction with the R groups on the enzyme's active site and the geometry fitting in, because certain interactions are encouraged and others are not. And so this is what makes it specific. This brings me to my next important concept, which is enzyme affinity. Now, enzyme affinity is effectively what I just kind of spoke about briefly. If I have my enzyme and I have my substrate, so my enzyme and my substrate, now, how likely is my enzyme to bind to this substrate? Now, one is collision theory, right? What is the probability they're going to bump into each other? That's one. But then affinity deals with how likely is this bond to take place? How likely is it that we form the enzyme substrate complex? That's the next question that we ask ourselves, right? Is can we go from this to this? And this then depends on what I just said. The bonds forming between the active site of the enzyme and functional groups, the chemical functional groups on the substrate. And this again depends on the geometry and the chemistry, right? So if my enzyme can very easily form this bond, if this bond can be formed very easily with this substrate, let's say sucrose, so if this enzyme can form this bond with the sucrose very, very easily, then we say that the affinity is high for sucrose, or the substrate that we're looking at, so let's say this is sucrose, is high. If this bond, so this ES complex, is not formed very easily, then we say that ES complex formed easily. And if we say that the ES complex is hard to form, difficulty, then we say that the enzyme affinity for this particular substrate, which I'm calling sucrose, is low. So effectively, these two principles is how enzymes work. Enzyme affinity, which is when the substrate bumps into the enzyme, how likely are they to form a bond? So you can think of your two hands kind of like interlocking right now. How likely is that going to happen? And the second is collision theory. Is the substrate going to find the enzyme? And so based on this, right, we're going to go and dive deeper into the Michaelis Menten equation. So to develop an intuitive understanding of Vmax and Km, we're going to look at the following scenarios. So I said that Vmax is the theoretical maximum rate of reaction. And so the reason I introduced the idea of collision theory is to explain rate of reaction. Rate of reaction talks about or describes a reaction in terms of the concentration of the reactants. So if I have A plus B that forms some molecule C, and I'm asking you what is the rate at which A and B form C, well, that is then dependent on, again, think of a box, right? Think of a box, think of your A molecules over here and B molecules over here. And to form C, the A molecules need to find the B molecules. And so the rate is then dependent on some constant and the concentrations of A and B. So what is the rate? Rate is concentration of A, concentration of B, times some constant K. And so when I'm asking you what is the maximum theoretical rate of reaction or the maximum velocity, it's dependent on what? The concentrations of the reactants. And so if you look at enzymes, let's say in a particular setup, I have 3 enzyme molecules. 4. Let's make it 4. Let's make it an even number. Let's say I have 4 enzyme molecules. Now, an enzyme can at one particular time, form an enzyme substrate complex with one substrate molecule. Correct? So the maximum theoretical rate is the one at which all the enzymes, this is important, all the enzymes are occupied, as in they're in the ES complex stage. That means the maximum theoretical rate is when all the substrates have done the following. This is the scenario that we're talking about. All active sites are occupied. Meaning that if I added more substrate, nothing would really happen. Nothing would really happen because the people working, by which I mean the enzymes, are all busy doing the task at hand. You can only do the next task if you are done with your current task. But all the enzymes are currently occupied. So when you give like some customer support like a call, right? Customer service support a call, and they're like, all our agents are busy. That basically means if I had like a room of 50 agents and all of them are on a call, then any subsequent person that calls that call center has to wait. They can't work faster than 50 calls at a time. So that's how enzymes work. That's what Vmax is, the theoretical rate at which all the enzyme molecules are in the stage of the ES complex, the enzyme substrate complex, because all the active sites are occupied. So even if I flood it with more substrate, they have to wait. They have to wait for what? They have to wait for their turn. Correct? And that essentially is Vmax. That rate of this, for example, for this enzymes, it's 4 substrates per unit time. That is the maximum rate. Right? The next thing to understand is the Michaelis constant, Km. Now Km is what? Remember? Half Vmax. Half Vmax, the substrate concentration at half Vmax. What this effectively means is at what substrate concentration are at least, so if my total enzymes are 4, so at what substrate concentration at least what? At least 2 enzymes, or 2 active sites, if you're thinking in terms of active sites, are occupied. It doesn't matter which 2, it could be this 2, or it could be, these 2, or it could be this 2. It doesn't really matter which 2 these are. What matters is what concentration of substrate, right? What concentration of substrate achieves this? That's what we're looking for. So Km is the substrate concentration at which at least 2 of the enzymes are occupied out of the 4. So the rate we're looking for is 2 substrates per unit time, right? And that is the intuitive understanding of the Km. So if I have a call center and there's 50 people, the Km value is at how many calls are at least half the people working. So at 25 calls are half the people working, because 25 would mean 25 out of the 50 workforce that I have are busy with a call. Vmax is what is the maximum rate I can work at. So if I have 50 workers, that means 50 people can pick up a call. That is the maximum rate I can work at. I can't work faster than that, and so if anyone else calls after that, they'd have to wait for their turn. But Km is how many calls are required to have at least half of my workforce busy. And that is 25 calls. So if I have 4 enzymes, what is the concentration of the substrate required to have at least 2 of my enzymes, so half of my enzymes, in an enzyme substrate complex stage, which is this equation. And so if we use these pieces of information, and then we look at what your rate of reaction would look like. So on a graph, it would look like this. You will see an initial linear increase. So if I increase the substrate, I am increasing the rate of reaction. Why? Because of collision theory. If I have more substrate, I am more likely to bump or find my active site. More likely to find my active site. But if I have less substrate, less likely to find, the probability of finding my active site is less. So the first thing we see by increasing the substrate concentration is that we see it increases kind of linearly. But then after a while, it plateaus. Why is this plateau happening? It's happening because of this reason. Vmax. All my enzymes are occupied. All of them are working. Correct? So because all of them are working, I can't work faster than that. So if I add more substrate, nothing will happen. And so this is Vmax. Vmax, the theoretical peak, the theoretical rate of reaction at which all the enzymes are occupied. Now half of Vmax would be somewhere, let's say here, right? Why would it be here? Because again, half of Vmax over 2, so just go somewhere like this, yeah? And then let's draw a line down to the substrate concentration. So what we see is this is our Km value. At this substrate concentration, half of my active sites, or in other words, enzymes, are occupied, meaning they formed the ES complex. Now you can notice that reaching Km happens at a much lower substrate concentration than reaching Vmax. You have to add a lot more substrate to then reach Vmax, but Vmax over 2, not so much. So this is not always like half and half substrate. This is very much dependent on the substrate, the enzyme, and the conditions of the reactions, etc., etc. This is the simplest explanation for building an intuitive understanding of Vmax and Km. And so now we introduce other nuances. We introduced other nuances like what happens if I add certain inhibitors. Now, there's a few kinds of inhibitors that you need to be aware of. Non-competitive inhibitor, competitive, and uncompetitive. Yeah. Non-competitive is not the same as uncompetitive. Just want to clarify that. And so, if we look at each one of these, let's start with our non-competitive inhibitor. So, non-competitive inhibitor. In a non-competitive inhibitor, what happens is, this is my enzyme, so I'm going to just copy that real quick. The active site is open. Active site is open, right? So a substrate like this can bind to this, right? The substrate can bind to the active site. But what happens is that we'll have this inhibitor, which could be a protein, which could be a chemical, bind to some other site on the enzyme, and what that will do is that it will change the shape of the enzyme. The site that it binds to is called the allosteric site. And so what this will lead to is something like this. The enzyme's shape is altered, but you see the active site is still there, unoccupied. So what does this mean for forming the ES complex? What does this mean for that? This means that if this is my normal, no inhibitor added, for my non-competitive inhibitor, what I will see is a decrease in what? Decrease in Vmax. Why will there be a decrease in Vmax? Because look at this. This shape is altered. Even though the enzyme's active site is not occupied, because the shape is altered, the enzyme is less effective. And so less of the total enzymes will work the way they're supposed to work. So your Vmax will decrease. But what happens to our Km? What will happen to the Km? The Km is unchanged. Now, why is the Km unchanged? The Km is unchanged because it will still take this much substrate concentration to form this enzyme substrate complex. it's only the fact that because less of the enzymes work effectively, the rate will be decreased. So let's say I have 50 workers in my call center. If 45 of those are fine and 5 of them are kind of sick, right? They're kind of sick. They'll still pick up a call, but they might not work really well. They might not be able to do their job, right? But it will still take 25 calls to what? To have half of my workforce busy. Does that make sense? Right? 50 people in my call center, 5 of them are sick, by which I mean the allosteric site is bound to the enzyme. So they might not be able to do their job. So my total output might not be 50 calls satisfied. It might be just 45 people satisfied and 5 people left unsatisfied, right? But it will still take 25 calls to have 25 people in my call center working. Why 25? Because that's half of the total. Half of Vmax, 25. So half of Vmax is Km, right? So what I will see in this graph, so let me just write down the Km, let's say Km is here. And let's say this is my non-inhibited curve. Oops. So if this is my new let me make this proper. So as you can see, my Vmax has decreased. But my Km value has remained the same. And so this makes sense, right? Even if 5 of the enzymes are sick, they're not going to work really well, but they're still part of the workforce. Which means that it will still take 25 calls. They're not completely out of commission, if that makes sense. They're not on holiday. They're still there, but they're just not working really well. So this is what happens to your rate of reaction in a non-competitive inhibition. Okay? The key takeaway is that there's a decrease in Vmax and the Km is unchanged. Those are the key takeaways. Now let's look at competitive inhibitor. Now, competitive inhibitor means that the enzyme's active site, is being competed for. So if this is the original substrate that we're interested in, and let's say this is our inhibitor. Now you can see that both the substrate that we have can form, so the substrate can form this ES complex. I'll write a star on it to show that this is the desired one. And then it can also form this. Why can it form this? Because it fits the shape. Oops. Let me get it again, sorry. There you go. So it can form this or it can form that. And so effectively it means that there's only one active site. So there's only one active site. So imagine this is our box. Imagine this is our box, and we have this and this. So which of these is going to find this active site first? Which of this is going to bump into this active site first? Right? Collision theory. Now, go back to what I said earlier, which is, okay, if I want to increase the probability of enzyme substrate complex forming, what do I have to do to my box? I have to add more substrate. So if I add a larger amount of my red substrate, oops, if I add a larger amount of my substrates, then what do you think, which one is likely to find, if I increase red, right? I've increased the red. Now, is red more likely to bump into this active site, or is the blue one? Which one is it? It's obviously the red one. There's a very high number of red substrate compared to the blue one. So the probability of that collision happening is higher, hence this desired EX complex forming is higher. Now what happens if I take the same box and I increase the inhibitor in this? Right? So okay. I increase it so much that there's so many blue molecules, that it's virtually outcompeting what? There's a lot more blue now and there's very little red. So the blue is going to form this ES complex. And this is all just going back to the collision theory, right? This is more likely to form. In the first case, this was more likely to form. And in the second case, this is more likely to form. So competitive inhibition is reversible because you can just increase your red. If I increase my red back to this original stage, wherein even though I have a lot of blue, it's still very little compared to the amount of red I have, then this ES complex forming's probability will be higher, right? So what does this mean for our rate of reaction? What does this mean for that? Okay, let's just copy this and let's change it slightly to explain and look at what would happen to the shape of the graph . So what happens to the shape of the graph? Let's use purple. The Vmax, right? The Vmax will be unchanged. Why is the Vmax unchanged? The reason the Vmax is unchanged is, regardless of what situation it's in, right? If I increase the substrate, that I'm interested in. So if I increase the red to such a large amount, so I'm gonna copy this. I'm gonna demonstrate this with the diagram. Right? I have so much red that virtually these three blue bumping into that active site is so low that it's close to zero. Right? The probability is so low that it's close to zero. Why? Because I have just an incredible amount of red substrate. So the probability that this happens is much higher. So much so that we can effectively say that blue is not there. This is me saying if a number x is so large compared to y that we can just say that x plus y is roughly equal to x. That's what I'm saying. So the maximum rate, because if I have 4 enzymes, right, them forming an ES complex this way, it's not going to be affected. It's not going to be affected at all, because blue is just not there. We're basically looking at the system where, like, yeah, blue doesn't exist per se. But what will happen is that the Km is increased. Now, why is the Km increased? The Km increases because what? You tell me. What is the Km? The Km is the concentration of the substrate at which half the active sites are occupied. But if I have this system, right, let's take this. If I have this system and I have, let's say, 10 substrate molecules, 7 substrate molecules, and I have, let's say, 4 blue ones. So now we look at this and we see that 4 blue molecules, they're not that far apart. 4, 7. So what is the probability that we form this ES complex? It's going to be roughly similar to forming this ES complex. Right? 7, 4, not that bad. So if I'm looking at my desired one, which is this, right? ES desired. If I look at this one, I will see that because of the competition for the same active site, at a particular time, at a particular point in time, what is the likelihood of this is lower, especially when the concentrations are similar. So the Km will be increased because at a higher substrate concentration, the likelihood of half of the enzymes forming active sites, forming ES complex with the red is what? So at a higher concentration, it's higher, right? At similar concentration to the blue, it's not going to be that high. So it will take more substrate to get to that desired effect, or that desired conclusion, which is like, half of the active sites are occupied. So what the graph will look like is, although the Vmax doesn't change, the Km, so if I just extrapolate this line, has moved where? The Km has moved to the right. And so this is desensitization. This effect we call desensitization. Or, in other words, we can say that the system is repressed. Why is it repressed? So moving the Km on a normal rate of reaction graph to the right means that the enzyme's desired activity of what we want, forming this ES complex and then ultimately forming these two products that we were talking about, right? Forming these two products is lower. Correct? So that's the effect that I need you to take away from this, which is, in the case of competitive inhibitor, depending on which you increase, either the competitive inhibitor or the substrate, the desired effect will be different, right? So Km will increase, so we'll move to the right, that we call desensitization, and the Vmax will remain unchanged, because if I do this, which is like such a large number of red substrate that effectively I can say that x plus y is roughly equal to x, then Vmax won't change. But on a smaller scale, when I have similar concentrations, then they're competing for the same active site. So for this correct enzyme, for the enzyme to pick up the correct substrate, and half of them to do that job, which is half of them pick the correct substrate up, the probability, the concentration will be to the right, because the probability will be decreased. So by increasing the concentration, we can get that desired effect. Now there's also something which isn't particularly part of A levels, but is good for completeness sake, which is uncompetitive inhibitor. Now in this case, it's the same kind of logic as a non-competitive inhibitor. The difference is the molecule that does this, the inhibitor that does this, doesn't bind to the enzyme like we see in the case of non-competitive inhibitor. It binds to the enzyme substrate complex. It binds to this. And so when it binds to this, effectively, what it does is it changes the shape and kind of prevents what? The formation of the products. And so if the products are not formed, right, then we're not finishing, if you remember the reaction I just mentioned earlier, we're not finishing that reaction. So we can't really consider it part of, the reaction. It's not going forward. This, where did it go? This part isn't happening. So if this part isn't happening, it's kind of messing up the whole system. So if you look at the graph then of something like this, if you look at the graph, so I'm just going to copy this and use this as the same template. What we see is that not only is the Vmax decreasing, but we also see that the Km decreases. And this is because the step of forming the products is hanging. In what? Hanging because the allosteric site, the uncompetitive inhibitor is binding to the allosteric site and then locking the enzyme substrate complex. So the enzyme, what happens to the enzyme? It's not forming the product. And if it's not forming the product, you can't reuse it. So if I can't reuse the enzyme, so effectively if I have my box, right, and I have 3 enzymes in it, one enzyme's like this, and the other, let me just paste this image. So one enzyme's like this, right? And the other 2 enzymes and the other 2 enzymes are like this, right? Yeah. So what this means is this enzyme, this one, will not return back to being reused, will not go back to something like, you know, just a plain enzyme, just something like this. It won't go back to being reused because it's stuck, it's hanging, it won't go back to this. While the other 2 will go back to this, this one cannot. And so what this means is if I have 50 people in my call center, 20 of them can't pick up another call ever again. So that means I only have 30 people working on the call center. You've decapitated them, the 20 people are gone, they can't do anything. They can't return. So that means I only have 30 people working. And so my Vmax is definitely going to be reduced. But my Km, which is at what concentration at 25 people, or what call number at 25 people working, also has to be higher, right? Because I have less enzymes. Go back to collision theory. I have less enzymes in the system. And so this is what uncompetitive inhibitors do. So if both the Vmax and the Km have decreased, Km and Vmax decrease, that's uncompetitive inhibition. But if just the Km shifts, by which we mean, you know, the Km has increased, then what happens? No, this one, competitive inhibition, right? So Vmax is not changing, and Km increases, so moves to the right. That means not competitive inhibition. And if Vmax decreases and Km remains the same, that means non-competitive inhibition. So all the information is right here. One thing I said Km decreases, but I moved Km to the right. That is wrong. I have to move it to the left. Why do I have to move it to the left? Because I said Km decreases. So when I said I have 30 people in my call center working, what is half of that? What is half of 30? What is half of 30? 15, right? 15. 15. So only 15 people can work. So the Km decreases. That's my bad. Sorry. Made the wrong graph. There you go. Okay. That's it. So Km decreases, Vmax decreases. Km moves to the left. When it moves to the left, generally that's a good thing. But in this case, it's not. Okay? So those are the 3 main things that we have. And so the next part is understanding where all of this comes from. So we can look at the derivation of the Michaelis Menten equation, but maybe let's just look at another way of drawing the same things that we just drew, the graphs I mean, which is, okay, this is a theoretical maximum rate, right? This is a theoretical maximum rate. So this will never be really achieved. So what is half of something that just keeps on going. Like this will kind of keep on increasing and increasing, you know, it's very so slightly. So that will change what my Vmax over 2 is. And so my Km value will always have this error in it. So what's another way of drawing this graph such that I can get accurate values for it? And so this is where we get the Lineweaver Burk plots. So for my competitive inhibitor, what would this graph look like? Now here's the thing. The Lineweaver Burk plot, what it does is that it takes the reciprocal of my y-axis and x-axis from what? From these graphs. So my reciprocal of the rate of reaction and reciprocal of the substrate concentration. So my x and y-axes are then inverse of the substrate concentration and inverse of the rate of reaction, which I'm writing as V. Right? And so what this does is that it changes the shape of the graph from something like this, which is like kind of non-linear, goes straight, then plateaus, to a completely linear line. And so you'll see something like this, right? If this is my normal control, so no inhibitor added, what is this point and this point telling us? So the y-intercept is, what is on the y-axis? 1 of rate of reaction. So what is this intercept? This is 1 over Vmax. Okay, the x-axis is the substrate concentration. So what is this x-intercept? This is 1 over Km. So to get Vmax and Km, you just take these values and then you just take the inverse or the reciprocal of that, right? So if this is, let's say, 0.1, then what is Km? Km is 10, because 0.1 reciprocal of 0.1 is 1 over 0.1, and so that gives me 10, right? So what will happen in when I add a competitive inhibitor? What will I see? So we know that in the competitive inhibitor, the Vmax is not changed, and I explained this in great detail earlier. But my Km, what happens to Km? Km increases, moves to the right, Now, if I draw that same thing on a Lineweaver Burk plot, what I will see is a line like this. It will go through the same 1 over Vmax, but the Km has shifted to the right. Now why is this? This is the new Km, right? Which I will write down in brown so that it's differentiable. Why is it moving to the right, closer to the 0? Well, remember, 1 over 10 is 0.1, 1 over 100 is 0.01. So if in the original case, where is it? If in the original case, it shifts to the right, this is a larger value. So when I have a larger value, I divide it, I take the reciprocal, I have a smaller value. So this would be your 0.01 and this would be your 0.1 as an example, right? So the closer you are to the 0 here, the larger your Km value and the worse your enzyme affinity is. Remember affinity? How likely is it that they're going to form a bond? It's not likely that they form the ES complex because the Km is shifted to the right here. If I then have my non-competitive inhibitor, what do I see? I see the same kind of, I'll copy the same graph. I'll remove the lines for the competitive inhibitor. Oops. So what do we learn about non-competitive inhibitor? What happens to the Vmax? The Vmax will decrease and the Km will remain unchanged. So if I draw this line, I will see that it will cross the x-axis exactly at where the other one does, but my Vmax will decrease. What is Vmax decreased in terms of reciprocal? Again, same logic, right? 1/10 is a larger number. So if my Vmax was initially 100, I would be closer to my 0, which is this point. But now, because the Vmax has decreased, which is 10, I will move further away. So my Vmax is right over here. And my Km will remain unchanged. For my uncompetitive inhibitor, because it effectively takes out your enzyme from the equation, what did we say? We said that the Vmax will decrease, and what will also decrease? Km. So if Km decreases, where is it going to move? It's going to move to the left. So now if I draw that, I will see this kind of behavior. So my Vmax has decreased and my Km has also decreased. Correct? And so this is all kind of what you need to know about Vmax and Km in terms of the Lineweaver Burk plot and in terms of the normal rate of reaction and substrate concentration graph, where I hope that it's clear to you what Km actually is. Km is the substrate concentration at which half the active sites are occupied. And I keep on repeating this. And I keep on making an analogy to a call center because I want you to think of it in terms of that. It makes your life so much simpler. But remember, I also said, remember this equation? Equation 1? This equation is what led to the derivation of the Michaelis Menten equation. I said this is the topic we're going to talk about, what? The Michaelis Menten equation. And Michaelis Menten equation, we've now developed an intuitive understanding of it. But now what we're going to do is we're going to derive the equation and then kind of connect the dots through that. So if I now have this equation 1, right? Enzyme plus substrate leads to the enzyme substrate complex, which leads to the enzyme being reused and the product being formed. Correct? Now, what we need to look at first, remember when I said a rate of reaction is A plus B leads to the formation of C, right? And then the rate is dependent on some constant K, and then the concentration of A and the concentration of B, collision theory. Now for us, right, the main step that leads to the creation of C, which is this, E plus P. So I can write my rate of reaction, my initial rate of reaction, as V naught equals, let me call this forward rate K2. Let me call this K1, and let me call this K-1. Now there's an assumption I'm making. The assumption I'm making is that there's no reverse reaction going back to the enzyme substrate complex from the enzyme end product. That is because we're only dealing with initial reactions. So in an initial reaction, we assume that there are no enzyme products, there are no products, hence the only way forward is through this, ES to K2, because there's no P. If I have no P, then I can have no reverse reaction. So it kind of simplifies our equation, right? So I can write my initial rate, which is this final step, the C thing that I've circled, as concentrate K2, some value K2, some constant K2, and then the concentration of E and S. So there's one assumption we've made, which is that it's the initial reaction where no product are formed, so no reverse reaction from E plus P can happen. This is the initial assumption that we're making. There's another assumption that we're making, which is, well, this is not an assumption, but this is just accurate, which is, what is the total enzyme concentration, ET? So the total enzyme concentration comprises of what? What does the total enzyme concentration comprise of? Right? It comprises of our enzyme and our enzyme substrate complex. Correct? So E total is equal to our enzyme concentration, right? This is the enzyme concentration, plus our enzyme substrate complex. Yep. So those are some things we're looking at. Now what we're going to do is we're going to try to derive the Michaelis Menten equation by using what we know about rate laws and some other assumptions that we'll make along the way. So what is the rate of formation? How do we form ES? That's the rate of formation of ES. Again, we're looking at this and we're looking at, so rate of formation of ES equals to K rate for ES, rate of formation K1, I'm calling that K1, enzyme concentration and substrate concentration, right? Then what is the rate of consumption of ES? ES can either go this way or this way. So I can write this down as K1, -1, ES, so it's just breaking down, plus K cat K2 ES. Right? These are the two ways that this can go. Right? And now there's another assumption we make. What is that assumption? The assumption is that in a steady state, the rate of consumption, this, is equal to the rate of formation, this. So I'm going to call this equation 2, 3, 4, and 5. So at steady state, what we say is that the formation of the ES complex is happening at the same rate as at the consumption of ES complex. So what I can do is I can equate these terms together. Right? So now what we're going to do is we're going to try to solve for ES. what that means is now I'll factor out ES. Why are we trying to solve for ES? Because enzyme substrate complex is the step that we look at for what? For this. We want to measure the formation of ES so we can measure what the rate of the formation of P, right? That's what we got this from. So to measure ES, we now have to separate ES over here. And what we see is K negative 1. I've just taken a common out. K2 equals K1 ES. And so what I can do now is I can take this value that I have, right? I can take this value and I can take it to the other side. So I have ES equals K1 over K negative 1 plus K2. So this is just the constant term, right? This is the constant term. E times S. Right? What is this? What is this? This term, so one thing to remember what Km is. Km is basically all these constants. It is K negative 1 plus K2 over K1. What do we see? What does this look like? What is this? What is this? This effect essentially is our Km, just inversed. So if I moved it to the other side and I brought my ES over here, so if I did this, for example, I could say that Km equals, because now this is just like that, this is just like that. Right? I could say this. Now remember what E was. Remember this E? Remember this? Enzyme plus enzyme complex is equal to total enzyme. So what I can do is I can say enzyme is equal to enzyme total minus ES. Right? I can say this. So I can move this and I can say Km equals E. So I can plug this into this equation and I can say Km equals E total minus ES, right? Brackets S divided by ES. Now, if I then, what am I trying to do? What did I say we're trying to do? We're trying to write an equation in terms of ES, right? So if I now try to separate ES from this, I will find, let's do that, right? So Km ES equals ETS minus ESS. So if I move this to the other side, I will say Km equals ES plus ES S equals E total substrate. So now I can take ES out of this. ES Km plus S equals ETS. Now this goes on that side. I'm just doing simple arithmetic, okay? ES equals ET S over Km plus S. Right? And so we get to this equation. Now, remember equation 2? The first thing that we said, V0 equals K2ES. What do we do with this? What do we do with this? We will plug this equation that we have over here into this. So my V naught equals, this is 2. So I'll plug this back in because I have an equation for E total, ES. So K2 equals ET S over Km plus S. Now, there's another thing we have to understand, which is Vmax. What was Vmax? What was Vmax, guys? Please tell me. What was Vmax? Vmax is the theoretical rate at which all enzymes are occupied. All enzymes are occupied. So when I am trying to look for Vmax through this equation that I have on top, instead of writing it like this, I will write Vmax as equation 2. Instead of writing it like this, I will write Vmax equals K2 times E total. What is this? My last equation. I will bring this and plug this in over here because Vmax equals K2 E total. And so now I see this equation. Vmax S over Km plus S. And so guys, this is our Michaelis Menten equation. And the only reason I did this derivation is to show you the thing about Km. So what did I say Km was? Km was the substrate concentration at half of Vmax. So let's do that. Half of Vmax. So we're saying that V0 equals half of Vmax. Right? That's what we're saying. So let's do that. And we'll see what Km is then. Okay? We'll do Vmax over 2 equals Vmax S Km plus S. Vmax cancels out. Km plus S equals 2S. Km equals 2S minus S. Km equals S. So this means that rate we defined earlier, Km equals this, right, is essentially giving us, at half of Vmax is giving us the substrate concentration. So at half of Vmax, Km is the substrate concentration. So if you read it off the y-axis, you should see it. You should see what concentration is required for half of Vmax. The other thing I want to note for you here is, this is the Michaelis Menten equation, right? This is the Michaelis Menten equation. So if I take this, and I take the reciprocal of it, for what? For the Lineweaver Burk plot. So 1 over V naught equals Km plus S. I've taken the reciprocal over Vmax S. Now this I can write as 1 over V naught equals Km Vmax S plus 1 over Vmax. Now, if I look at an equation of a straight line, y equals mx plus c, c being the y-intercept, we see that the y-intercept, which I've been talking about over here, is 1 over Vmax. And we see that in this line, so I'm just going to draw it out, in this graph, right, the y-intercept is 1 over Vmax. My x is the substrate concentration, so this is 1 over S is the substrate concentration, 1 over V naught is the y-axis, right? And what is my m? My gradient, Km over Vmax. So that means this is increasing at Km over Vmax, right? The gradient. And then what is my x-intercept? Well, that's very easy. If I say x equals 0, if I say y equals 0, right? So y equals 0, I'll have negative 1 over Vmax equals Km over Vmax S. The Vmax cancels out. And so I see negative 1 over Km equals 1 over S. So this being my x equals negative 1 over Km. Negative 1 over Km. Remember, I said this is 1 over Km, but remember it's on the negative side. So this is always negative, right? But here, through maths, through just basic maths, we have shown why it is, right? At y equals 0. And so guys, this is a very, very comprehensive understanding of enzymes and the Michaelis Menten equation. And I hope this helps. If you have any questions, do let me know. Otherwise, take care. Ciao, ciao.